we're going to start the next section on experimental concepts and further ideas. And the first talk is Juan Garcia-Bellido with an ultra high frequency solid state detector proposal. So yeah, you can go on, please.
Thank you very much. Do you all see the fireworks? Okay, so you might wonder, since many of you know that I'm a theoretical cosmologist, what am I doing here in this session of experimental aspects? No, this is only due to my friend Fernando. Fernando heard about this idea that we were developing with Miguel Montero like a decade ago. It's still in the drawing board. You will see many things are rather sketchy. But he insisted that I should present this at the workshop. So I'm going to give you a very simple-minded approach to the idea. So I'm sure there will be plenty of discussions afterwards. Most probably this will not get to anything real, no, any particular specific detector, but let's discuss the ideas, okay? So let me first present what I think are the main lines of my presentation. First, I'll discuss the cosmological and astrophysical sources of in the range of megahertz to gigahertz. In order to determine whether we can measure this, I'll ask myself, what are the physical properties and requirements for detection of these sources? They could be both stochastic gravitational backgrounds or individual events. And the question that I'll pose is it possible to measure this with solid state detectors? Obviously, the main part of the talk will dwell on this. The discussion that will ensue is whether there are, what are the experimental prospects, what are the type of crystals that I have in mind in order for the detection of these gravitational wave backgrounds. And finally, I'll give you a summary. So many of the sources have been already discussed before in the theory sessions. Let me very briefly mention preheating. Now we know also from Andreas and Carlos, you could also look at the thermal plasma after inflation and look for gravitational wave background from there. There are obviously the cosmic strength and topological defect, which has been discussed several times, among others this morning by Geraldine. But then I would discuss a little bit more about planet mass range primordial black holes, either produced from large fluctuations or some other mechanism like the ones we're exploring now. Not just the events, but also the stochastic background from them. And finally, any other process, some of which have been envisioned by Richard in his talk, as long as you have a comoving size of the horizon, which is between 10 meters and a centimeter, you will be in the gigahertz to megahertz range. So anything that may happen at that scale in the universe that had that size might be relevant here. So we're open for all possible sources. Now, what about the astrophysical or local sources? Now, let's think of primordial black holes with masses between 10 to the minus 7 and 10 to the minus 3 solar masses. Let's assume that they are in dense clusters in our galactic halo. This is something which might take some time, and I leave for the discussion afterwards. Just to begin with, something that I promised Sebastian to discuss was, imagine that we fill up our halo with 1/100th of all the dark matter needed into this type of black holes, 10 to the minus 5 solar mass black holes, right? Plus or minus 2 orders of magnitude up and down. Then we can ask ourselves, what is the dark matter content in the neighborhood of the solar system according to the rotation curves of the galaxy, our galaxy? And you see that it's about 8 10 to the minus 3 solar masses per parsec cube. And this translates immediately for this fraction of PBHs in the total fraction of the universe in dark matter to about 1/10 of a parsec. And this depends very much on how dense the local concentrations of black holes are. For instance, if you have an enhancement or density contrast of 10 to the 9, then you would have something like a milliparsec or smaller. And therefore you might well be within the solar system size, okay? So there might be one black hole of 10 to the minus 5 in the solar system. So that's pretty near, okay? And this may play a role in the discussion we have afterwards. So there are two ways in which you could see this scenario, these local sources. One is by having these black holes find each other. This is much more rare. They have to be near each other to lose energy and finally become bounded. It depends how dense these concentrations of black holes are. But then they're much more copiously produced if you have a close hyperbolic encounters. Okay, these are not bounded systems, so this would happen in any cluster of black holes, and they just simply inevitably they pass each other. If the impact parameter is sufficiently small, they bremsstrahlung a gravitational wave. Okay, it will be like a burst of gravitational waves, just like kinks in strings or cusps. So let's look at the general scenario of primordial black hole formation. Typically, you assume that the same mechanism that generates the fluctuations we observe in the CMB on very large scales also happen on small scales if you have some feature in the potential. We discussed this in the context of Higgs inflation. There are some references here. Now, of course, there are immediate consequences of such a kind of feature because it produces diffusion, quantum diffusion of the field around that period. And this generates very long tails, exponentially decaying tails, which enhance the probability of collapse. But not only that, so make it more probable to produce black holes, but not only that, they also enhance the correlation function. So it means much more probable to find black holes near each other and therefore collapse to form clusters. So the usual monochromatic and uniformly distributed constraints that you see in all textbooks or now in reviews by Carr, Kuhnel, and others, you would see a monochromatic constraints at different mass scales. That's completely obsolete because we know that doesn't work. We cannot have, except for very small windows, black holes of those masses. So if we want to think about, say, solar mass, 100 solar masses, or even 10 to the minus 5 solar masses, that picture doesn't hold. However, it's very natural that those black holes, as I was describing, because of the non-trivial exponential tails, have a broad mass distribution, and also they're clustered, especially clustering clusters. Now, here, the only thing that one requires is more or less a scaling invariant spectrum, much larger amplitude, and let the universe expand. Because the evolution of the number of relativistic degrees of freedom, so how much pressure there is in the plasma, the collapse or disappearance of some of these degrees of freedom at the electroweak scale, at the QCD scale, at the plus or minus annihilation, all of this produce a decrement in the number of degrees of freedom, produces a decrement in the equation of state. It can reach even about 0.2, and depending on the matter content at the QCD epoch, for instance, you can even reach lower. And this enhances the probability of collapse in an exponential way. If your equation of state, which affects the critical collapse density that sets the scale for collapse, is reduced, then it's much more probable that even a small amplitude would collapse to form a black hole. This is kind of the arguments that I was using in my discussion with Geraldine just a while ago. So if you just take the standard thermal history of the universe and you convert that into a mass spectrum, you see that there are peaks very dominant at the QC scale. That's because there's a very sudden drop in the number of degrees of freedom when quarks and gluons combine to form protons. But then there are also secondary peaks at 10 to the minus 5 solar masses. This is the ones I'm after. There are other peaks at about 100. This could explain some of the LIGO and Virgo events. And there are peaks about 10 to the 5, 10 to the 6 solar masses, which could explain the centers of galaxies, the primordial seeds from which galaxies started to form. So, but let me concentrate first on the 10 to the minus 5 solar masses. Just to give you some extra support to the idea, if you superimpose in the mass distribution of events that we have from LIGO Virgo, the GWTC2 catalog, soon we'll have the GWTC3 with many more lines here, and you also add up that we can measure from microlensing events, you see that there is a concentration right around our proposal. So perhaps there is some support to the idea. So let's go beyond. Let's think about smaller masses. So as I was saying, there are two categories. One is a binary coalescence. The other ones are hyperbolic encounters. Let me first go through binaries. Out of the tremendously exciting observation of gravitational waves by LIGO and Virgo in 14th of September 2015, we know we just opened a new window into the universe. Now we can look for the masses of black holes with very high precision, as you will see, with gravitational waves. Okay, we don't have to wait to see the mass accreting on a black hole and emitting X-rays, no? The low mass X-ray binaries, for instance. We can directly measure through the effect of the emission of gravitational waves, the masses of black holes as they merge. Okay, and they have this specific chirp pattern. Now, the chirp has a maximum frequency where it has maximum amplitude at about 2.2 megahertz for masses of order 10 to the minus 3 solar masses. And if it's 10 to the minus 5, it's even larger. It could be on tenths of a gigahertz. Okay, so this is the realm that we're discussing here. So between 10 to the minus 3, 10 to the minus 7 solar masses, we would have events, would have chirps with frequencies right at the detection of these experiments, with amplitudes which are not tremendously suppressed. For 10 to the minus 3 solar masses, 10 to the minus 23, 10 to the minus 5 is 10 to the minus 8. So for 10 to the minus 5 solar masses, it would be 10 to the minus 25. So, but this is all at 1 megaparsec. And I was discussing just a while ago that even if you could reach your window, your horizon, all the way to a megaparsec, still there are many events that could happen within our halo. And we're talking about parsec to kiloparsecs, okay? So we could have a tremendously enhanced amplitude and therefore probability of detection if we look at events that may happen around us, in the halo of our galaxy. Now, the maximum frequency also gets related to the maximum gravitational wave flux, okay, through this expression. This gives you about 10 to the 48 watts. And this, remember, because of the dependence on mass and frequency, especially at the highest frequency, this is essentially dependent on mass. So this would be true for 1 solar mass, it would be true 10 to the minus 5 solar masses. This was mentioned yesterday. And I completely agree with it. So the flux in our detectors would be about 10 to the 10 watts per centimeter square at a distance of a megaparsec, much bigger if you're much closer, obviously. So that's for inspirals. What about hyperbolic encounters? I was saying that imagine that you're in these dense clusters, two black holes, they approach each other, they bremsstrahlung, they are accelerated. This is a current of mass here. You're accelerated and produce a burst of gravitational waves. It's not very directional, like in the case of electromagnetic bremsstrahlung, it's very broad. So there's a chance we might see this very clearly. And there are some of the references discussed here. But let me concentrate on what are the values of the eccentricity parameter, which is going to be relevant for the amplitude of the gravitational wave signal. For mass of about 10 to the minus 6 and velocity of, say, 100th of the velocity of light, so in near approach, and a distance of order 10 to the minus 8 astronomical units, we were thinking about black holes, which would be 1 per, say, solar system. If these find each other, say, in the solar system, and they're much more highly concentrated, that it might happen that 2 of these might reach each other at a distance of about an astronomical unit or even smaller. And depending on how much smaller these distances are, impact parameters, you might have a very important emission of gravitational waves. And how does it look like? It's just simply a burst. In power, it's a very narrow, and you can compute what's the typical time duration of these bursts. For the parameters that I was describing, so for these distances and these masses, you get something like a millisecond. If you happen to be, say, very near the, say, parabolic, so for a given range of masses, you might reach this, then you can even make it smaller. So sharper in time, 10 to minus, so tens of microseconds. So the power and the strain gives you amplitudes, which again are for 10 to the minus 23, for 10 to the minus 3 solar masses. And it gets into linear with mass. The frequency here is slightly more complicated. It has to do with how quickly these two objects pass each other. And this is in the gigahertz, again, for mass of order 10 to minus 3 and distances of order 10 to minus 8 astronomical units. The flux received on Earth from these individual events, okay, it's 10 to the 10 watts per centimeter square, only if you have essentially a speed of light approach. If you have much smaller velocities, that means larger impact parameters, so further distance from each other, then the velocity very quickly decreases with the power 10. So you might quickly suppress this. So probably would not even be measured. But let me leave the formula there for us. No? So if we look for in this plane of changing the impact parameter, and we ask ourselves, what is the typical amplitude? No? And what's the typical frequency? We reach the frequencies between megahertz and gigahertz for this type of distances between us, the two black holes at the maximum approach. And the typical amplitude goes from 10 to the minus, so this is in 10 to the minus 20. So this is about 10 to the minus 19, and this would be 10 to the minus 23 or so. So in the range of 10 to the minus 19, 10 to the minus 23, and with in microseconds, you would be around 10 to the minus 2 microseconds or so. Okay, so very short duration, very high frequency, and very powerful emission of bursts. So what are the physical requirements for this solid state detector? First, we need sensitivity in the megahertz to gigahertz range. That's clear. We need very quick response times in the microseconds. Remember that it's a very relatively small gravitational wave flux received on Earth, so we have to be very sensitive to a few, so a small power being left in the detector. That depends on cross-section, of course. And we need to screen other sources: thermal, cosmic rays, radioactivity, magnetic fields, etc. So here's the proposal. So let's think of solid-state detectors. Let's think of first, what are the necessary ingredients? What are the microscopical properties of these crystals? First, imagine something like this crystal of table salt, chlorine, sodium chloride. You can ask yourself, okay, what is the speed of sound? This is the kind of quantity that will play a role in the cross-section. The larger the speed of sound, the larger the probability of conversion of a gravitational wave into a distortion of the network of atoms, no? The net. You also want to know the refractive index, okay? You want to know what's the melting point, whether you can build sufficiently large monocrystals, and some crystals are much better than others for producing these monocrystals. I'll describe later why I insist on monocrystals. You want to prevent impurities and dislocations to hide your signal. You need to know your lattice spacings. You need to know your energy levels if you want your band structure. So this is what we were thinking of 10 years ago with Miguel Montero. So you have a gravitational wave that impinges on a crystal. And this generates, through its polarization patterns, motions, very tiny motions, 1 part in 10 to the 23, 10 to the minus 25, distortions in the positions of atoms. You say, okay, you're not going to see that. I mean, the typical distance between the atoms, it's 1 angstrom. How are you going to see 10 to minus 15 of this, right? Of course, you have to take into account that this is a solid crystal. And you could ask, are there coherent motions of the solid crystals? What we call phonons, okay? So if you distort the network of atoms in a coherent fashion, when you have successive waves of gravitational waves distorting the position of atoms, you could transfer part of that energy into the phonons, and the phonons eventually be detected on the surface of the crystal, okay? So that was the basic naive thought, no, that came to us. Now, we have worked out in a work which is still unpublished, and Fernando has seen the draft, others have seen the draft. I'm not going to go into the details. We worked out a full Hamiltonian, quantum Hamiltonian. We worked out what was the network of atoms, the dual basis in momentum. We worked out what was the typical band structure, what that was needed for the detection of this. And the bottom line is what is the probability of conversion of a gravitational wave into phonons. And this is what one can compute using Fermi's golden rule, one particle production of phonons in this case, okay? This standard quantum mechanical formula you use, for instance, quantum field theory. After some lengthy calculation, you end up with a quantity that depends essentially on the properties, macroscopic properties of the solid, on some polarization tensor contractions, which are order 1, and then on phase space quantities. I will deal about the last term in a minute. But let's suppose for the moment that this is a wave which enters the crystal. It encounters some resonance in the frequency of oscillations of those atoms, so in the phonons, with a given momentum which is collinear with the lattice, the dual lattice, no? Characterized by B. So you can ask in n dimensions. For the moment, we didn't concentrate on, I mean, we thought first of graphene. We realized later that the power is not good enough for graphene. It's probably best to have a crystal. So you gain a lot by going to higher powers of dimensions. Crystal obviously has a bigger dimension than a plane. And with using this property, assuming for simplicity, but not necessarily, a cubic lattice with equal sizes of the spacing, lattice spacings, A, and length of the crystal. This could be a big macroscopic crystal of 20 centimeters or so. The dispersion relation that we choose was one that was linear with momentum. That is, we're in the acoustic band, okay? And we assume that the linear proportionality is related to the speed of sound, and we have very large speed of sound. So we are looking for crystals that would be very compact and with very large speed of sound. For instance, diamond. We'll see later, sapphire is probably the best option. Right? So if you look at this term, of course, if you have zero momentum, you would be on a resonance, and this could give you a very large, it's 1/0, a very large amplitude of probability of transfer. But typically that doesn't happen. This is a small but not negligibly small, so you can expand the second order, and by expanding the second order, you get this expression for the rate of phonon production. Remember, it goes like the size of the crystal over the lattice spacing to some power. So for graphene, this would be 2. For crystal, this would be 3. Okay. Now, what's the power detected? Well, remember here it's 1/h bar, so you can multiply by h bar omega.
5 minutes.
And excuse me?
5 minutes.
5 minutes.
Yes.
Okay, thank you. So let's imagine we have a monochromatic plane which impinges. We can ask what's the cross section, and the cross section has a form shape which is very similar to that found by Grischer, say 40 years ago. So let's think what are the experimental conditions that we need. Let's recycle monocrystal detectors like those of DAMA and NANAs for cold dark matter, WIMPs, and put some detector superconducting detectors on the surfaces of these crystals, have them packed into a size of 1 meter cube. Okay, this is of course science fiction for the moment, but not the 20 centimeter one. And let's be specific about the type of solid that we have in mind. So let's think of sapphire, for instance, which is a very compact one. It's aluminum oxide, Al2O3. It has a larger speed of sound. It's not as big as diamond, which is about 40 kilometers per second, but it's one of the largest. We have a relatively small, this is what we want, a lattice spacing of 5 angstroms, a typical mass here of 10 to the minus 26 kilos, so it's a mass of 20.4 in units of mass of protons. A shorter radius of 10 to the minus 53, and this gives you a cross-section in the millibars. So let's ask, of course, about the large speed of sound, where it's come from. We have here the photon-phonon band structure. We are concentrated on this for the graphene, for sapphire, this band, okay, the acoustic band. And for this, the power at the detector would be about 1 × 10 to the 19 watts, so very tiny. Of course, at 1 megaparsec. If we have a source at a 10th of a parsec, this could be huge. We have a gain of 10 to the 7 square, 10 to the 14. So it gives you 10 to the minus 5. And then we are talking business. Then we can ask what are the chances we see this. What's the rate at the detector for a mass of 10 to the minus 3 is about 10 to the 8 phonons. For 10 to the minus 5 solar mass would be 10 to the 6 phonons. At a distance of a 10th of a parsec, this gives you 10 to the 20 phonons per second. And that is significant. That's something which is worth looking for. And how would you look for it? Well, putting at the edges, at the surfaces of these detectors, some superconducting devices. And here I'm describing something which was very recently published and got my attention, which was published the 30th of September this year, what's called self-calibrating superconducting pair breaking detector. So this would be able to detect single phonon at the surface. So they use the band structure and the properties, superconducting properties of the detector to measure the arrival of the phonons and correlating in time those arrivals. And I think this would be extremely important for chances of detection of such a background. So what are the main sources of noise in the detector? I mentioned this, impurities and dislocations in the monocrystal. That's why we want very carefully grown monocrystals, like you can do with sodium chloride, or you can do with sapphire. There are companies that do this, and they can be big enough. Some of the mirrors that will be put in the Anton telescope will have 200 kilos. Okay, so we're talking about big crystals. So possibly there's a chance that we might use that technology to create the detector. Of course, another source of noise is the phonon scattering and lifetime. So from the moment they are created inside the crystal to the surface, they have to live long enough and not being scattered to look for correlation properties of those phonon arrivals. You want those phonons not to decohere, and this is at the speed of sound, those phonons will reach the detectors in 10 to the minus 4 seconds. So that's quite long enough that there could be some decoherence on the way. So one has to be careful about this. And I'm sure many experimentalists know much more than I do on this subject, and I might propose solutions to it. There's always the thermal noise. Fortunately, if you think of detectors which are separated, well, I thought I had here another slide, which are separated and isolated, then you could look for a emission or detection which is not coherent. So the thermal noise fluctuations would go away. I mean, you would see a signal rather than noise. Of course, there's the interaction with superconducting detectors, and there are unknown radiative sources and cosmic rays which harm you. There is a possible improvement that we discuss in the paper, which is to use the Van Hove singularity. And this has to do with the very specific directions in which the solid may be, so that the gravitational wave momentum, so wave number, just impinges on the solid right where there is a special resonance, what's called the Van Hove resonance, with a momentum that exactly coincides with that of the gravitational wave. If this happens, then there is an enhancement of the phonon band near the singularity. There's a very large density of states, which you can compute by doing this approximation around that band. And you can see that it's 1 over the square root of this. So when you are around, so when the frequency exactly coincides with that resonant frequency, you have an enhancement of several orders of magnitude. So for this, you need a gravitational wave burst that has some width. Where you can ask what's the effective direction of the signal. That would be integral over frequencies of such a width. You can then compute the number of photons produced. This is this integral, where you have the rate of photon production from a gravitational wave from the previous expression. And then you see that you get exactly the same expression as before, except with a speed of sound, which is not that of the solid, but it's enhanced by this extra factor. And this could give you an enhancement of order 10 to the 6 beyond. So if you thought that you would not be able to see any gravitational waves with a certain experimental setup, you might hope that somehow the direction of the gravitational wave will impinge on the crystal in certain direction, which will make it much larger. So you would be able to directionally tell where the source came from.
Juan, would you like
to? So let me end
here.
here.
Okay.
Let me end here with summary. Thank you, Vet. So there are cosmo and astro sources of ultra high frequency gravitational waves in megahertz, like I was describing from primordial black holes. Typically, they're very weak, and in the case of close hyperbolic encounters, they are very short bursts of gravitational waves. Fortunately, there are some tentative solid state detectors. I described Sapphire. I'm sure we could open the floor to discussion of what other crystals could be of use. At least we found that these in certain realms could work. But of course, we need to screen all the sources of noise. And this is something which I'm not an expert. And hopefully the experimentalists in the audience might help with improving the setup. With this, I finish. Thank you very much for your attention.
Thank you, Juan. That was super interesting. There is a question by Michael.
Yeah, yes, thanks for your talk. First, this is phonon resonances. The first phonon resonance is in infrared in Sapphire. Is that what you're talking about, or you're talking about making the crystal resonant like a resonant bar?
Yeah, I was thinking of making it resonant like a resonant bar. So look for frequencies that will exactly coincide with that of the gravitational wave and be more sensitive at that. Yeah, and then.
Okay, so there, Weber had a theory of a quantum theory back in the old. I met him once in Pakistan a long time ago, and he was talking about it then.
And that was discussed by Grishuk. I remember I have a paper, a very interesting paper, that he claims that Weber was
to do with correlated quantum effects in the material, which seemed, and there was an enhancement factor, which made him explain how he could, the events that he claimed. It seems similar to your enhancement factor.
But it's not my enhancement, no. We followed Grishuk's criticism of Weber's results, and we have the full Hamiltonian, quantum Hamiltonian. Yes. We computed the rate of events, and we made the corrections, and we agree with Grishuk, by the way. So there is a suppression, at least there's no such enhancement as Weber was proposing. But nevertheless, in crystals of the size and properties that I was describing, this still can give you an enhancement which is large enough to be used for detection of gravitational waves, according to the numbers I gave.
So it will have to be a crystal, not a metal.
It would have to be crystal, yeah.
Yeah,
that's right.
There was only one I remember, Brzezinski once made a sapphire resonant bar. We have small sapphire resonant bars.
What size were those crystals?
Well, Brzezinski's one, it's in his book, I can't remember, it was quite big. We've got some crystals which we've been using, but I'll show that in my talk anyway.
Great, great to hear.
So
well, maybe this has already been discussed before. Yeah.
No worries. Yeah.
Sorry, so we can maybe continue with that very interesting discussion. I also want to ask you some things, Juan, but I think it's time, so we moved to Francesco Sorge talk on, do you want